Hello, ladies and gentlemen. So today we are going to solve three problems. The first problem is on the transfer function, okay, of the state space representation of the mechanical system shown below. And the next equation will be on pole placement method. Okay, the next question will be on a pole placement method to find the matrix again K. And then our last problem will be on determining or verifying if the system is stable or unstable given the input matrix A. Okay, so let's start with our first problem here. So the question reads, state space equations for a mechanical system are given by the equations below. Obtain the transfer function for the system from the state space equations. So we are given the state space equations. Okay, so we have the state equation, which is the first one, which is x dot 1 and then x2 dot is equal to the matrix A there. Okay, which is a 2 by 2 matrix because the system is a second order system. 0, 1, negative k over m, negative b over m, and then the state variables x1, x2, and then of matrix B, which is for the input matrix there, and then we have the output equation, which is matrix C, the state matrix there, I mean matrix C, and then you have x1, x2, which are the state variables. Okay, all right. So now, we start. So the question reads, so first of all, we list our matrices given here. So matrix A is given by, let me just reduce the size of this. Matrix A is equal to 0, 1, negative k over m, negative b over m. Okay. And then matrix B is equal to 0, 1 over m. Okay. And then we are also given matrix C. Just a minute. Okay. And then we have matrix C. Okay, so matrix C is given by 1, 0. Okay, so these are the important information. First, we have to gather. Now we have to find this the transfer function. Okay, the transfer function of the state space equations is given by. Okay, remember the transfer function is simply the ratio of the output to the input, right? So output divided by input is equal to matrix C multiplied by, okay, SI, where I is the identity matrix, and then minus matrix A, the inverse of this, and then multiplied by matrix B. Okay, when the initial conditions are what is 0. Okay, so this is a transfer function. So we know matrix A, we know matrix B, as well as matrix C. Okay, so the first thing we have to find is actually this matrix there. Okay, so let's first find that matrix. So SI minus A. So what is SI minus A? Okay, so identity matrix here. Okay, so our I matrix is our 2 by a second order system. Our matrix A is 2 by 2. So our identity matrix will be 1, 0, 0, 1. So let us substitute there. So you multiply this identity matrix multiplied by S. So we get it S 0, 0, S. Okay, minus And then matrix A. So matrix A is 0, 1, negative K over M, and then minus B over M. So let us subtract these two matrices. Okay. So remember, with subtracting matrix, you subtract the corresponding elements, right? So S minus 0, that is S, or the adjacent elements. S minus 0, that is S. And then 0 minus 1, that is negative 1. And then 0 here minus negative K over M, that is positive K over M. And then S minus negative B over M, that is S plus B over M. Okay, so that is Si minus A. Now, let us get the inverse of that, okay? So the inverse of the 2 by 2 matrix, okay? So the inverse of a 2 by 2 matrix. So we have to find the inverse of matrix A. Okay, let's say matrix X, or whatever it is, right? The inverse of matrix X, okay? This is equal to what? The adjoint of matrix X, okay? The adjoint of matrix X divided by the determinant of matrix X, okay? So for a 2 by 2 matrix, the adjoint of the matrix of a 2 by 2 matrix is a matrix that you get when you exchange the elements in the major diagonal and then multiply the elements in the minor diagonal by negative 1, okay? So we're going to exchange these elements in the major diagonal. We exchange the coefficient, okay? So this is an adjoint matrix. Okay, so this S plus B over M, we take this position. And then while S will take this position. While this becomes negative K over M. And this becomes positive 1. Okay, so this is our adjoint matrix. And then we're going to divide this by the determinant. So what is the determinant of this matrix? Okay, so we're going to divide by the determinant. So what's the determinant of a 2 by 2 matrix? Okay, the determinant of a 2 by 2 matrix, which is matrix Si minus A, simply the product of the major diagonal element minus the product of the minor diagonal element, right? Okay, so we're going to multiply these elements. Okay, so the product of this minus the product of that, right? Okay, so let us replace that. Let's find the product of that. So that is S times S plus B over M, that is S squared, right? Plus B over M times S minus the product of K over M times negative 1. Since we're subtracting, this will become positive K over M, isn't it? Okay, positive K over M. Okay, so this can be written as, okay, so I'm going to write this guy 1 over S squared plus B over M by S plus K over M. And then I'll multiply this by the matrix, which is the adjoint matrix, okay? So the adjoint matrix is S plus B over M, and then negative K over M, and then here 1, we have S here. Okay, so this is it. So what we found here is Si minus A inverse. So we found Si minus A inverse. Okay, so we found this matrix here. Let me just take it here. So you have 1 over. So what I'm going to do, I'll multiply this guy here, the determinant. I'll multiply both on top and down by M. Okay, so I don't need to clear out the fraction here. So you notice that what I'm going to have here, you're going to have M on top, right? If I multiply both on top and down by M, here you have MS squared, right? Okay, and then you all here just remain with the B times S, and then plus the K, okay? And then multiply by the other matrix there. The matrix is S plus B over M, and then 1 minus K over M, then S. Okay, so this is Si minus A inverse. Now let us multiply this now by the next matrix, okay, which is B, okay? So let us multiply by matrix B, okay? So multiply by matrix B. So this is now be Si minus A inverse multiplied by B. multiplied by matrix B. Okay, so never mind, don't distribute this factor inside here, just complicate your work. Okay, so just leave it there. So ms squared plus bs plus k. So I'll bring this matrix here, s plus b over m minus k over m, and then 1 fs, and then multiply by matrix B. Okay, matrix B is given by 0, and then this is 1 over m. Okay, 1 over m, that is matrix B. Okay, let's check. Yeah, so that is the matrix B. Now we have to multiply these two matrices. Okay, so remember the multiplication matrix is a row by column, right? Okay, so it's row by column. So this is the 2 by 2 matrix. This is a 2 by 1 matrix, right? So the result of matrix will be what? 2 by 1 matrix. Okay, so the result of matrix will be a 2 by 1 matrix. Okay, so let us multiply this. So row by column. So we're going to have S plus BM times 0, that is 0. Okay, and then plus 1 by 1 over M. So this will become the first element here. You have 1 over M, right? And then the next row, again, you're going to have negative K over M multiplied by 0, that is 0 plus S times 1 over M, that is S over M. So the product of these two matrices now is given by that. Okay, so our SI minus A inverse times B is simply equal to M, okay, divided by M S squared plus BS plus K, okay, and then multiply by the matrix 1 over M, and then S over M. Okay, now we multiply by matrix C now. Okay, so let us include matrix C. So we need matrix C now. Okay, C SI minus A inverse times B. So matrix C, remember, is 0, meaning 1, 0. So this constant value, which is the factor here, I'll write it outside. Okay, the determinant. Okay, ms squared plus bs plus k. Okay, and then matrix C 1, 0, and then this product of SI minus A times B is what? 1 over M, and then S over M. Okay, so we have to multiply these two matrices. So this one is 1 by 2 matrix, right? That's the order of this, 1 row, 2 columns, and then this is 2 rows, 1 column, right? So you notice that the result will just be 1 by 1 matrix, okay? So let us multiply these two matrices. So we have 1 multiplied by 1 over M, and then plus 0 multiplied by S over M. So the result of these two matrices just be 1 over M. Okay, so you have M ms squared plus bs plus k. Here just end up having what? 1 over M. Okay, so at this point now, you can multiply M multiplied by 1 over M, isn't it? Okay, so M multiplied by 1 over M here. So you get what? So this is a C SI minus A inverse times B. So this, the result of this just becomes M and M will cancel out. Just have 1 on top here, and then divide by, okay, M S squared plus BS plus K. Okay, so this marks the end of our problem. So therefore, we can say the transfer function, which is defined by the output over input, okay, which is the equal to C multiplied by SI minus A inverse multiplied by B is simply equal to 1 divided by ms squared plus bs plus k. Okay, so we are done with the problem. Now let us see, look at the second problem that we have been asked to find. So this problem is on the pole placement method. Okay, so let me just share the question. Okay, so let me just share the question. Okay, so here's our second problem. Okay, so let us deal with it. So here's a question. So the question reads, for the system given by that, output over input is equal to 1 over s times s plus 1 times s plus 2. The system uses the state feedback control, u is equal to negative kx. Let us choose a desired closed loop pose at that, okay? And then determine the state feedback gain matrix k. So pole placement method works in such a way that you want to place your pose at the desired location, okay, on the S plane, whichever desired location you want to place them, okay? So we want to find the value of k that is going to place our pose at those desired location. Which locations? S1 at the, those S1 and S2, which are the complex pose, and also S3 should be a negative 10, okay? So now, for us to do that, we have to make sure that our system is controllable, okay? Meaning that we're able to maneuver, we're able to take pose to whatever desired location. So we need to find the value of k so that k will be able to place our pose at that desired location. Okay, so the condition is that the system must be completely state controllable, okay? Because if something is controllable, you are able to control to move it from one point to another. So must be able to take pose to whatever location, whatever location you desire. So let us find that matrix K, okay? So I can give you an illustration. So this is a diagram I want to share for you. So this is how this diagram looks, okay? Okay, so this is how this diagram looks. So you have this, okay? So we want to find that matrix K, right? As okay, that's a feedback, okay, matrix. Again, K, okay? So that we'll be able to place the pose of that state matrix A, its pose at the desired location on the S plane. Okay, so let us do that. So that a couple of methods actually there are 3 methods that we can use to do that. But here in this video, I'm just going to focus on the method which is the easiest. I find the easiest. I don't know which other methods people maybe can find it easier, but this one I find it the easiest. Okay, the direct comparison method or the substitution method, whatever call it. There's another method which is called Akamatov method. Okay, it can also be used. All right, so we're going to use a direct substitution method here. All right, so first of all, we have to find matrix A, B, and C, okay? Though C is not necessary, but we have to find matrix A and B. So I give you the transfer function there, okay? So you have the output, y of S over the input, u of S equal to 1 divided by S plus 1 and S plus 2, okay? So first of all, we have to expand this, okay? You can see this is a third order system, right? So if you expand this, you're going to end up having what? Expand the denominator, you have s cubed, right? Plus 3s squared plus 2s, okay? So this is what you get, okay? Now, from this, I'm sure you know that from the transfer function, you can write your system in the controllable canonical form, okay? So let's write our system in the controllable canonical form. So let's get matrix A. So in the controllable canonical form, what is matrix A? So it's a 3 by 3 matrix because the system is a third order system. So you see that we need to have A naught here, right? We need to have something like A naught, but it's not there. The constant, okay? The constant is not there. So we need, this is A naught, this is A1, this is A2, okay? So our A naught is not there. So the first row here is 0, 1, 0. This is standard for controllable canonical form. And then the second row here is 0, 0, 1, okay? And then the third row here, you have A0, which is not there, okay, which is 0, and then A1, negative A1, of course. So this is negative. These have to be multiplied by negative, okay, in the third row. So negative A0, negative A1, negative A2. So here you're going to have negative 2 as negative A1, and then negative 3. Okay. And then our matrix B is standard, okay? So matrix B actually depends on what you have on top there, right? So since you have just 1 there, so this will be 0, 0, 1. If you had a 2, maybe, I mean, if you had a 2, this was going to be 0, 0, 2, and so on and so forth, okay? 0, 0, 1. And then matrix C is actually standard matrix, okay, which is 1, 0, 0, okay? All right, so this is what we get, okay? Now, let us write our equation, the closed loop equation, okay, for our system here. So we need to make this comparison, okay? The closed loop system, Si minus A plus B times K. So we have to find the determinant of this, of the closed loop equation, okay? And this is equal to, okay, the equation, okay, or the characteristic equation where the poles have been desired to be placed, right? Okay, mu1, mu2, and then mu3. So this is a characteristic equation, the closed loop characteristic equation, right? Okay, must be equal to the closed loop characteristic equation where you're given the poles already, okay? So we have to make this comparison here. So what is K? This matrix that is the one we need to find. So K is simply equal to, since it's a third order system, so we're going to have 3 values of K. So K1, K2, and K3. It's actually a row matrix, okay? A row matrix, a 1 by n matrix, okay? So this is our K here. So let us find this Si minus A plus B times K, okay? So what is Si? Remember I here, it's a 3 by 3 matrix because of a third order system, okay? Our I now looks like this, right? 1, 0, 0, and then 0, 1, 0, okay? 0, 0, 1, okay? Now let's multiply that guy by S. So we're going to have S 0, 0, and then 0, S 1, 0, 0, S, that's Si. Oh, so this is 0, okay? Minus A, our A matrix is simply 0, 1, 0, and then 0, 0, 1. That's 0, negative 2, negative 3. Okay, and then plus B times K. So our B matrix is simply 0, 0, 1. And then our K matrix is simply K1, K2, K3. All right. So let us subtract these two, okay? So let us subtract those two matrices first. So S minus 0, that is S. 0 minus 1, that is negative 1. And then you have 0 here, you have 0 here, you have S here, you have negative 1 here, you have 0 here, you have positive 2, and then you have S plus 3, okay? And then let us multiply those two matrices as well, okay? So this is a 3, okay? This is a 1 by 3 matrix, sorry, a 3 by 1 matrix, okay? 3 rows, 1 column. This is a 1 row, 3 columns, right? So our result matrix must be a 3 by 3 matrix, okay? So let us multiply, okay? So this row is going to multiply all the matrices there, right? So 0 multiplied by K1, and then 0 multiplied by K2, and then 0 multiplied by K3. That's the first row we're going to get, okay? So our first row will be 0, 0, 0, okay? Similarly, here again, it will be 0, 0, 0. And then we have K1, K2, and K3. Okay, now let us add those members. Okay, let's add those two matrices. So we have S, negative 1, and 0. Okay, and then you have 0, S, negative 1. Okay, and then 0, 2 plus, sorry, this is K1, sorry, okay. This is K1, 2 plus K2, right? And this will be S plus 3 plus K3, okay, plus K3. Now the next thing is to find the determinant of this guy, right? Remember, we have to find the determinant of this whole thing, right? So since we have found that guy, now let's get its determinant. Okay, so we need to the determinant of this matrix now, just from calculating. So S -1, okay, and then 0, 0, S -1, okay, and then K1, 2 plus K2, S plus 3 plus K3. Let us get the determinant of this, okay? So how do you get the determinant of the matrix? Remember here, you have to alternate the sign. So positive minus positive, right? So the determinant of this guy, so have to form what we call what? The cofactors, right? Of the matrix. So this S, you multiply S, multiply by what? The elements that are not in the same column as S, and then same row as S, right? So this matrix here, it's a matrix that remains, okay, which is S -1, 2 plus K2, and then S plus 3 plus K3. And then the next will be minus, because there's a minus. Now here, this -1 again has a minus. So minus minus will plus. So +1, I'm just going to leave it out. It's just 1. And then if I cross out that column and that row, you see the matrix that you get is 0, -1, K1, S plus 3 plus K3. All right. Now, let us simplify this, because the last one just be 0, because we won't have 0 multiplied by the matrix that you're going to get, right? So it won't have any effect, okay? So you simplify this. So this is the S, okay? This S multiplied by what? Okay, the determinant of these guys, right? So this multiplied by that, right? Okay, okay. So S multiplied by S plus 3 plus K3. So you have S squared plus this other guy, just write this as 3 plus K3. Since they're constant, I'll multiply both of them by S, right? Okay, like that. So that's the product of these two, right? And then minus the product of what? -1 by that. So since we have a minus there, and another minus that is going to come here, and this minus over will be positive, right? That'll be plus 2 plus K2. Okay, I hope that is clear. Okay, so let us multiply that. Okay, and then here, when it comes to this matrix, this one multiplied by that, that will be 0. Okay, and then minus this multiplied by that, negative K1, that is positive K1. Okay, so we can now expand this. So this will be S cubed plus 3 plus K3, S squared plus 2 plus K2, S, right? And then plus K1. As you can see, we get the third order equation, okay? Now, the next equation, the equation to the right, which is this one here, we have to replace the pose that have been given to us, okay? So I've been given the pose, okay? So the desired pose are given here. So let us list them, okay? So S1 or mu1, okay, those are the pose, right? So S1 is simply equal to -2 plus J 2 root 3, right? And then my S2 will be equal to -2 minus J 2 square root of 3. And then S3 is just equal to -10, okay? Now let us form the characteristic equation for this. So S minus, okay, mu1. So mu1 is what? That guy, right? Which is -2. So minus, that'd be +2, right? And then minus J, okay, 2 root 3. These are subtracting. So minus, this will be plus, it will be minus, right? Okay. And then multiply by S minus mu2. Okay, so again, you're going to have S plus 2. This one becomes plus, right? Plus J2 root 3. And then S minus C, that, which is negative 10, that is plus 10, right? Okay, now we need to expand here. Let us expand. So if you want, you can multiply one by one, right? S multiplied by S, and then S multiplied by 2, S multiplied by whatever, blah, 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 and all that, right? But what I'm going to do here is this. Okay, I'm going to work in reverse. Remember, this came as a result of solving something, right? Okay, so what you need to do, just put these guys, these first two numbers, the way they are, you see them in square bracket, in brackets, right? And square them, right? So that is it. S plus 2 squared, right? And then also, what is this guy? This number here, plus. So I'm going to put plus always, okay? What is this number here? This number is actually the square root of 12. So when you square it, it just becomes 12. So what you're going to do, you can just square this number here and get it out, right? That is 4 by 3, isn't it? So that is just 12, okay? So this is it, 12, right? Okay? You can verify. So imagine you are solving an equation that has this, right? And they are equating to 0. You notice that you're going to have S plus 2 squared equal to negative 12, right? Okay, just verifying. You can see I can find those poles, right? And then taking a square root of both sides, right? Taking a square root of both sides, what do you have? You have S plus 2 here equal to plus or minus the square root of negative 12, right? Okay, so you take 2 the other side, you're going to have S is equal to negative 2 plus or minus the square root of negative 12. This can be written as what? Negative 3 multiplied by 4, right? Isn't it? So what is the square root of 4 here? The square root of 4 is simply 2. So that guy can go out. So negative 2 plus or minus 2. What is square root of negative 3? It's just complex. That's J, right? So J root 3. So you just move the reverse, okay? All right, so that's a shortcut you can do so that you avoid wasting time expanding each one of them, right? Okay, so this these two factors are just equal to that, okay? So that guy multiplied by S plus 10, okay? Okay, so let us simplify. So this is S squared, right? Plus 4S plus 4, and then plus 12, right? Which is just be equal to 16, right? So that can be combined as 16. And then multiply this guy by S plus 10. So let's multiply now. So S squared by S, that is S cubed, plus S squared by 10, that is 10S squared. So we're done. And then 4S by S, that is 4S squared. And then 4S by 10, that is 40S. And then 16 by S, that is 16S. 16 by 10, that is 160. Okay, so let's add like terms. So we have 14S squared plus 40 plus 16, that is 56. S, and then plus 160. Now, according to this equation here, we have now to equate these guys to each other, right? Okay. So let's see, equate those two guys to each other. So we have this characteristic equation, which is S cubed plus blah, 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 and whatever, and then this other equation. So we start with the first one. So S cubed plus, okay, so what is here inside? That is 3 plus K3, okay? 3 plus K3 multiplied by S squared, and then plus, the other one is 2 plus K2 S, 2 plus K2 multiplied by S plus K1, right? And this is equal to S cubed plus 14S squared plus 56S plus 160. Okay, now it's just a matter of comparison here, right? The terms of S squared must be equal to the term of S squared here. The term of S must be equal to the term of S, and the term of K, or the constant, must be equal to the constant here. So clearly you can see that K1 is simply equal to 160, right? And then we can also solve for K2. So 2 plus K2 should be equal to 56, okay? So from here, you can see that K2 is equal to 54. And then 3 plus K3 should be equal to 14. So clearly here you can say that K3 is equal to 11, okay? So therefore, our feedback gain matrix K is simply equal to K1, K2, K3. So K1 is 160, our K2 is 54, our K3 is simply 11. Okay, so this is the end of our second problem. So now let us look at the last question. Okay, so I'm going to share the last question of today. Okay. So this is the last question of today. Okay, so the question reads, for the system given by that, where the matrix A is given and B is equal to that, determine whether the system is stable or not. Okay, so for the stability of the system, we actually need to know where the poles are located. Okay, that's one of the ways to know to know the stability of the system, to know about the stability of the system. It depends on the location of the poles or the system itself. Okay, the opening of poles. So now we have to find the poles of this. So the poles of a matrix, okay, of such kind, I know that it's actually equal to the eigenvalues of that matrix. So in simpler terms, we have to solve for the eigenvalues, okay, of our given matrix A. Okay, so the eigenvalues. So let's find the eigenvalues. The eigenvalues of the matrix, okay? So the eigenvalues are given by the determinant of what? Lambda I, where lambda is eigenvalue minus C matrix A. Determinant of this guy, right? Must be equal to 0. So our I is a 3 by 3 matrix. So adding matrix. So multiply by lambda. So you notice that we're going to have lambda 0, 0, 0, lambda 0, 0, 0, lambda, right? Okay. And then minus matrix A. So matrix A is given. Okay, matrix A is given, which is 0, 1, 0, 0, 0, 1, -6, -11, -6, right? So let's subtract this. So lambda minus 0 is lambda 0 minus 1, that is -1. And then we have 0 there. And then you have 0 here. We have lambda of -1, okay? We have 6 here. We have 11 here. We have lambda plus 6, okay? So we have to find the determinant of this guy, and it must be equal to 0, okay? So let's get the determinant of this. So I'm sure now you are used. So this is plus, minus, plus, right? So plus, minus, plus, okay? So this be lambda multiplied by, okay, this small matrix that we form, which is the product of this multiplied by the product of that, or minus the product of that, right? So can you quickly do that? So the product of that major diagonal, that's the lambda squared plus 6 lambda, okay? And then minus, okay, 11 by -1. So that is positive 11, isn't it? Okay. So that's what we get. And then in the second one, okay, we multiply by -1, so cancel that one will be 0, multiply by that, and then minus that, right? Product of those two. So that just be +6, okay? And this should be equal to 0. So let me just expand. You have lambda cubed plus 6 lambda squared, 11 lambda plus 6 equal to 0. So now here, you need to do what? You need to solve this equation. So if you have a calculator, well, good, okay, you can solve this polynomial. But if you don't have a calculator, a third order polynomial is easy to solve, okay? All right, so what you need to do here is to actually find the factors or the numbers that you can substitute in that polynomial, and it will be equal to 0. That polynomial will be equal to 0. So what number can you put for that polynomial to be equal to 0? So you notice that here, no positive number will make this polynomial equal to 0. There's no positive number you can put there and make this polynomial equal to 0. The reason being is that if you get any positive number here, you would see that this one become positive when you cube it. Whatever number put there, there's a value of lambda if it's positive. It's positive, this is positive, and this polynomial need to be equal to 0. Okay. So the only values that can make this guy equal to 0 are the negative values. Okay, the negative values. So definitely you can see that the negative values of lambda will make this polynomial equal to 0. So already you can tell that this system is stable. So we just have to find those values of lambda, which are the pose. Okay, you can tell that this system is what? Stable. From this, just this by just analyzing this. Okay, so no positive values can make this equation equal to 0. All right. So now, the way we do it, okay, is to look at the constant, the factors of the constant, okay? The factors of the constant. Okay, so you're going to try the negative values of the constant, of the factors of the constant. So this constant is 6. What are the factors of 6? Okay, this 6, you want to find the negative values. Remember, we're just focusing on the negative values of it, right? That will make up 6. So negative 1 and negative 6 itself. Okay. And what else? This 6 again can also be written as what? Negative 2 and negative 3. What else can we have there? I think that's all, isn't it? Okay. Those guys will produce 6. So let's try one of them. So let's try negative 1. Okay. If this guy is equal to 0. So we're going to have negative 1, the power 3, plus 6 by negative 1 squared plus 11 by negative 1 and then plus 6. This is equal to 0. Right? So negative 1 cubed, that's negative 1. That is 6 because negative 1 squared, that is just 1. This is negative 11 and then plus 6. You can see that this is 12. This is negative 12. So you end up having a 0. So you can tell that negative 1 is one of the numbers that can go into what? That. So if you are trying this as a factor, so you can say that lambda plus 1. Okay? Because when you solve for lambda, you get negative 1, right? Is it a factor? Is one of the factors, right? Okay, is one of the factors. Okay, so we need 2 more factors. It's a third order system, so we need to have 3 factors. Okay, all right. So the other 2 factors now can be gotten by either a long division method or I'm going to use a method I call it synthetic method. Okay, so what I'm going to do for synthetic method, I feel it's fast. Okay, I feel it's fast. Then I'm going to draw a table. Okay, I'm going to draw a table like this. All right, so here I'm going to put negative 1, which is a number that I first tested, right? Negative 1. And then here, I'm going to write the coefficient of our equation. So the coefficient of this cubic equation. So I'll write 1, I'll write 6, I'll write 11 here, and then I'll write 6 here. And then the first number here, I'll put, for the first value here, coefficient, I'll put a 0. And then I'll add these numbers, right? So 1 plus 0, that is 1. Okay, and then to find these other numbers, I'll be getting whatever that I add multiplied by negative 1. So negative 1 by 1, again negative 1. And again I'll add 6 plus negative 1, that is 5. Again I multiply negative 1 by 5, that is negative 5. Okay, and then 11 plus negative 5, that is 6. Okay, and then negative 1 by 6, that is negative 6. Okay, so if you need negative 1 as a factor, the result of these guys, the last numbers you add must add up to 0. Okay, so indeed this is equal to 0. So now you have reduced the polynomial now from third order to second order polynomial. So you see this one now to be lambda squared, 5 lambda, and then it will be a constant. Okay, so we have our new polynomial as what? Lambda squared plus 5 lambda plus 6. So if you do another synthetic division, you're going to have just a linear factor. So you can actually factorize this one, isn't it? Product 6, sum 5, and then you see that those are just factors of 6, right? Which is positive 2, right? And then positive 3. So meaning complete factorization of this polynomial is lambda plus 1, lambda plus 2, and lambda plus 3 equal to 0. So you can see that the values of lambda are equal to negative 1, lambda equal to negative 2, lambda equal to negative 3. So from this, since you can say that these lambda values are negative, are found on the negative side of your complex plane, right? Which is S plane. Okay. they're found here. So we have the pole here at -1, the pole here -2, and the pole -3. So all the poles are located in the what? So this is it. Sigma axis. Okay. This is you can say your omega axis. Okay. Very cool. All right. So you can see that this the poles are found to the negative side, right? Okay. So this system is what? Stable. Stability, right? So we have that kind of a system, right? Okay. Which decays with time. Okay. Decays with time. So that's the stability of the system. Okay. So this marks the end of our today's meeting. Thank you so much for your time. Okay. So we meet next time. God bless. Okay.